So here's a fun little problem to start out with. It's easy to state and pretty easy to understand, but it'll turn out as pretty hard to solve. So what we're doing here, just like it says, is we're going to flip a coin 10 times. So there's a coin with some needless animation flipping 10 times. And the question is, what's the probability that you won't end up with 2 straight heads? So as you can see in this little example, we did end up with 2 straight heads. And while you could pause the video at this point and work it on your own if you felt like it, maybe I'd caution you that it's a pretty challenging problem. Although it'll turn out with a little bit of guidance, I think that anybody watching this will be able to figure it out. It doesn't involve any advanced mathematics or any techniques or formulas that you're probably not familiar with already. Big picture, when you're talking probability, what you're trying to figure out is how many ways can this thing happen, divided by how many total things could happen. The cardinality of the event space divided by the cardinality of the sample space if you want to be really fancy. The total number of ways to toss the quarters, that's going to be really easy, right? Because there's just 2 ways to toss a given quarter, either heads or tails. So if you're doing it a whole bunch of times, you're just multiplying together a whole bunch of 2s. However, figuring out how many ways we can do it without getting consecutive heads, that's going to be harder. For that, we might need a little bit of help.
Consider smaller cases.
Thanks, pup. That's actually really good advice, though. It'll be overwhelming to try to figure out how many ways you could flip 10 coins without getting consecutive heads. But what if it was just 1 coin or 2 coins or something? That'd be a lot easier. Maybe if we study these smaller cases, we can start making inferences about the larger cases. Let's start with the simplest example, where we're just flipping 1 coin. Well, it could flip as heads or tails, so that gives us 2 options. And since we're only flipping it once, there's no way to get consecutive heads, so both of those options would work. What if there were 2 coins? Well, 2 options for the first coin, 2 options for the second coin. That gives us 4 total options. However, one of those 4, the one that's just heads, contains consecutive heads, so we have to throw it out, leaving us with just 3 possibilities for 2 coins. Moving right along, what if there were 3 coins? Well, 2 possibilities for each of the 3 coins leaves us with 2 times 2 times 2, or 8 possibilities. However, 3 of them now contain consecutive heads, so we need to throw those 3 out, leaving us with just 5 that fit our criteria. All right, so as instructed, I considered smaller cases, but where do I go from here? It seems like I'm throwing out a different amount each time. Am I supposed to look for a pattern there? I need some more help.
Define each case in terms of the 2 that precede it.
Okay, that makes sense. So the idea here is if we only have 3 coins, it's easy enough to just list all of the different possibilities. But when we have more coins, we won't be able to list them all because there'll be too many. So what we want to do is pretend we didn't have the list of all the different ways you could flip 1, 2, and 3 coins without coming up with consecutive heads, and try to come up with the number of ways we can flip 3 coins without consecutive heads, knowing only the number of ways we can flip 1 and 2 coins without coming up with consecutive heads. Is that doable? Well, sure, because you can't flip 3 coins without coming up with consecutive heads without first flipping 2 coins without coming up with consecutive heads. So we'll start with our list in blue of 2 flips and then just think about what the 3rd flip can be. The low-hanging fruit is just to tack on a tails, because if you haven't made consecutive heads in your first 2 flips and your 3rd flip is a tails, there's no way you're going to have consecutive heads in your first 3 flips. But now we got to be careful. That 3rd flip could also be heads, but we can't just go tacking on a heads to each of the options that we see listed in blue, because it's possible that tacking on a heads as that 3rd flip will create consecutive heads. In fact, we can only have our 3rd flip be equal to heads if our 2nd flip was tails. But that's problematic, because remember, my goal is to figure out the number of things in my purple list, knowing only the number of things in my red and blue list, not listing the objects in those lists themselves. So without actually listing them, how can I figure out how many of the different combinations in my blue list end with a T? Because if it ends in tails, then and only then can I tack on a heads as the 3rd flip. Well, that's easy. Just look at your list in red. If you want to end up in the list in blue and end with a T, just start with the list in red and tack on a T. So the number of items listed in red will be the same as the number of items listed in blue that ends with a T. To those items ending in T, we can now tack on an H to get the remaining elements in our purple list. You follow all that? Because it got a little tricky there at the end. In fact, it's probably the hardest thing we'll do in this entire video, but it's also the most important. We can figure out how many ways we can flip 3 coins without getting consecutive heads by just adding up the number of ways we can flip 2 coins without getting consecutive heads and the number of ways we can flip 1 coin without consecutive heads. And it turns out there's nothing special about getting 3 from 1 and 2. We can figure out the number of ways we can flip any number of coins without getting consecutive heads by finding the sum of the number of ways we can flip 1 less than that number of coins and 2 less than that number of coins without getting consecutive heads. Let me demonstrate. As we've seen, there's 3 ways to flip 2 coins without getting consecutive heads. And there's 5 ways to flip 3 coins without getting consecutive heads. That should mean that there are 5 plus 3 or 8 ways to flip 4 coins without getting consecutive heads. Either you don't get consecutive heads on your first 3 tosses and then your 4th toss is a tails, or you don't get consecutive heads on your first 2 tosses and then your 3rd toss is a tails, in which case your 4th toss can be a head. Let's check our work by listing out the 16, 2 times 2 times 2 times 2, ways that we can flip 4 different coins, then getting rid of all of the options that contain consecutive heads, and sure enough, we're left with exactly 8 combinations. We can even match those 8 to the 8 that we came up with using our algorithm. Maybe now you can start to see the light at the end of the tunnel. Let's make a table. It's easy enough to just count the number of ways that we can flip 1 and 2 coins without getting consecutive heads, those numbers being 2 and 3 respectively. Then to figure out the number of ways you can flip 3 coins without consecutive heads, just add that 2 and that 3 to get 5. Want to know the number of ways to flip 4 coins without getting consecutive heads? Well, you just add together the number of ways you can flip 2 and 3 coins. And we can continue in this fashion to fill out the rest of the table, figuring out a given term by just summing the 2 previous terms in the table. And depending on just how math nerdy you are, you might recognize a pattern in those numbers. Arguably the most famous sequence in all of mathematics. These numbers we're coming up with appear to be the Fibonacci sequence. And that's not a mirage, these numbers actually are the numbers in the Fibonacci sequence. And that makes sense because the way we're generating them, summing the 2 previous numbers, is exactly how you come up with subsequent terms in the Fibonacci sequence. So the fact that we were lucky enough to start out with 2 consecutive terms in the Fibonacci sequence, namely 2 and 3, is going to guarantee that all subsequent terms in our table are Fibonacci numbers, which makes it really easy to fill out the rest of the table. And now that we know that there's 144 ways in which you can flip 10 quarters without getting consecutive heads, we're ready to answer the original question. Recall that the probability of not getting consecutive heads in 10 flips of a quarter is equal to the number of ways in which we can flip 10 quarters without getting consecutive heads divided by the total number of ways we can flip 10 quarters. So the numerator of this fraction is 144, and the denominator, as we saw earlier, is just made up of the product of a whole bunch of 2's, 10 of them to be exact. Finally, we rewrite 144 as 12 times 12 because each of those 12s can be rewritten as 2 times 2 times 3, which allows us to cancel out some 2's and get 9/64ths, or roughly 14%, as our final answer. Nothing especially exciting about the answer, but I feel like the process there is kind of cool. I'll leave you with a related question that's kind of fun once you learn this process. What would be the probability, if we're still flipping 10 coins, that you don't end up with 3 consecutive heads? Feel free to post solutions, thoughts, questions, methods in the comments if you feel like it.